Let's start with a statement of the completeness theorem. The Gödel completeness theorem says that formal proof and logical implication coincide. So on the one hand, if we can prove a formula from a theory, this formula is logically implied by the theory. And we've already proved this, and we've seen this is called soundness. Now, conversely, whenever a formula is logically implied by a theory, there's a formal proof for that formula. So, in short, T proves phi if and only if T logically implies phi. One direction is, as I said, soundness, and we've already proved that. So from here to here, we already know. The harder direction is going from here to here. And that's what we embark on now. We will prove this direction of the completeness theorem in form of the model existence theorem. So what does this say? Well, we saw that T proves phi formally if and only if the set T union not phi is inconsistent. So if I add to not phi to the theory T, or rather the universal closure of not phi to T, then this becomes inconsistent. Assume now T does not prove phi. We want to show then, right, because that's the direction of the incompleteness theorem, we want to prove by contrapositive. So we want to show that T then does not logically imply phi. To show this, we need to find a model for this set or this theory here, T union not phi, right? Because if we can find a model for this, then that means that this logical implication does not hold. By the equivalence above here, so by this equivalence, however, we know that T union not phi is consistent, right? Because we assume that T does not prove phi. So to prove completeness, it suffices to show the model existence theorem. If a theory is consistent, it has a model. So then we could apply it to this theory here, and we would get that it has a model, so we would know that T does not logically imply phi. The big question is now, of course, how do we find such a model? Pretty much out of the blue, because all we have is really the theory, right? In particular, we can ask, is there a canonical model of a theory? Well, if you think a little bit about it, we know that every L term represents a possible value in a structure. So if you want to give a model of a theory, you have to at least be able to assign every term, right, a value in the structure, right? So we need to be able to interpret at least the terms formed using only constant symbols. So let's collect those terms in a set. Let's call that set K. So K is the set of all L terms that don't have any variables. And then the idea would be, well, we need to interpret these, be able to interpret these terms, right, in a structure. So why not make these terms our universe, right? So we don't even have to worry about what should be our universe because we need to interpret them, these terms, so why not let them be our universe right away? Well, we have to be a little bit careful, so not so fast, we can say here. We need to take into account facts that T proves about K. So for example, in field theory, we can prove that 0 plus 1 is equal to 1 plus 0 times 1. So these are both terms on the left side and the right side that don't feature any variables, so they would be part of this set K here. But the theory of fields, right, from the field axioms, we can prove that these terms actually are equal. So in our intended universe, we need to identify these terms. So let's do that. right? So for terms s and t, we say s is equivalent to t if and only if t proves that s is equal to t. We first need to verify that this is actually an equivalence relation, and that's precisely what you need the equality axioms for. So it's not hard. Take a look at the equality axioms and then show that this is indeed an equivalence relation. So once we know that this is an equivalence relation, we can take the equivalence classes and we denote the equivalence class of a term t by square bracket t. And now, instead of taking the terms directly, we actually collect the equivalence classes of a term in a set. Each term in K has an equivalence class, and we collect that in a set A. And this now will be the universe of our structure. The structure A, or also denoted by A sub t. So term models here refers simply to the fact that the universe of our structure will be given by the terms, or rather the equivalence classes of terms. Equivalence given by what t tells us it can prove about equality of terms in there. So now we have the universe of our structure, but in order to make it a full structure of our language, we also need to interpret the non-logical symbols of our language over this structure. Right? And the way we set this up, it pretty much suggests itself how we should proceed here. So first of all, of course, every constant symbol interpretation should just be the equivalence class of that constant symbol. Similarly, we need to define what the application of a function symbol to elements of our structure is, right? The elements of our structure, keep in mind, are equivalence classes of terms. So what should the application of a function symbol f be, right? Well, that's just the equivalence class of the term ft1tn. And finally, right, for relation symbols, right, when should the relation R hold between equivalence classes t1 to tn? Well, it should hold precisely when t tells us it holds, namely if it can prove that this relation holds between the terms t1 and tn. And you already see here this might actually be a problem later on, because t might not actually be able to be expressive enough. So this could cause problems down the road. T might not be powerful enough to settle all the relations, so we might actually miss defining some relations that we should down the road. So this foreshadows a little bit what we'd have to do later about T, but we'll get back to that in a couple of slides. So now we need to verify that this definition does not depend on the choice of representative for each equivalence class here, right? Because we're actually using the representative here to define, for instance, the value of this function application here. And again, just as before, you take a look here at the equality axioms. Right? Remember, these equality axioms also included the congruence for functions and relations, and that's precisely what you will need here. So once you've verified this, we've actually seen, we actually see that all these definitions then are well defined. We get a structure, and this structure, right, that we get this way, we call the canonical term structure of a theory T. Okay. So we now have a structure defined that is somehow related to T. And the hope is that this structure, A sub T, so the canonical term structure, would be a model of T. And if we were only concerned with atomic sentences, that's actually true, because it holds that for atomic sentences sigma, this sigma is true in A sub t if and only if t proves sigma. So for atomic sentences, A sub t is a model of t. And you show this by first showing that for every term, the interpretation of that term in our canonical term structure A is just the equivalence class of t. Right? And you show that for all t in K. And as usual, you show it by induction on the height of t. And then you prove the theorem by just considering the two cases for atomic sentences, right? Separately. Of course, we would like to extend this theorem or this proof now inductively to all L formulas or L sentences. Well, we would use, for example, in the case of negation, we would need to use that AT models not sigma if and only if AT does not satisfy sigma. Right? But we would need to be able to connect this now to the proof side. So it would need an analog there. And that analog would be that T proves not sigma if and only if T does not prove sigma. Right? And that's precisely the property of T being complete. Right? So if you recall complete theory, for every sigma it proves either sigma or not sigma. Now similarly, right, the equivalence, right, in the inductive step we would extend in another inductive step to formulas with an existential quantifier. And here we would use the equivalence that AT satisfies exists X sigma if and only if there exists a term in K such that AT satisfies sigma if I plug in, right, if I evaluate the variable X as the equivalence class of the term T. So this again would need an analog on the syntactical side. And in that case, it would be T proves there exists X sigma if and only if there exists a term in K such that T proves sigma with T substituted for X. Okay. Theories with this property have a special name. They are called Henkin theories. So this is the so-called Henkin property. And this will play a crucial role, as you may imagine, in the proof of the completeness theorem. And what we need to show now, and that's the work ahead of us, is that T can be extended to satisfy both of these properties without changing the provability properties of or consistency properties of T in any way. Right. So that's the project ahead of us. Can we extend T to be complete and also to have the Henkin property?